Hi, I'm Nicholas, and in this video I will present our research paper, OctoPack, Instruction Tuning Code Large Language Models. The motivation for this work was that code large language models only excelled at continuing code, but not at following instructions related to code, such as in the example on the left, where we asked the model to explain us some function, but then it just provides us with the function itself. It might also go off and do something completely different, overall not addressing our query. Meanwhile, for non-code large language models, instruction tuning has been very successful to make them closely follow user-provided instructions, such as in the example on the right, where we get the model to provide us a detailed explanation of a question, even in an entirely different language. So how can we apply this instruction tuning paradigm to code models? First, we need a good dataset, a dataset that relates code data to some human instructions. To do so, we turn to commits. Commits pair some code before with a commit message that relates to some change that was made to that code, and then the code after. So we have this triplet that relates two pieces of code with a commit message that describes what happens when we went from the code before to the code after. And commits are available in abundance, and thus we create commit pack of 4 terabytes of scraped commits that we take from GitHub. They all stem from commercially licensed repositories to ensure that there are no problems with using them downstream. We also only focus on single file commits to make sure that there's not too much complexity, because with multi-file commits, the commit message is bound to be not very specific because there's many more changes. And then also we filter out very low quality commits, such as merges, where the commit message is literally just merge this and that. Below is a distribution of commit pack. It covers hundreds of programming languages. And we also create commit pack FT, which is a 2 GB high quality selection of commit pack. It only contains commits that really resemble instructions, such as increase something, do something, this and that. And all of the commits in there do not have any external references to make sure that it is self-contained. And also the commits are it only contains commits that have messages which are very detailed by specifying certain word limits. And this also ensures that it is higher quality and more specific and more useful for instruction tuning. Below is a plot of the task distribution of commit pack FT according to GPT-4. So now that we have the data, we need a benchmark to track whether or not our instruction tuning with code models is working. To do so, we create HumanEval Pack, which is an extension of OpenAI's HumanEval to 3 different tasks and 6 different programming languages. The tasks are fixing code, as depicted on the left, explaining code in the middle, and also synthesizing code. So for fixing, we ask the model to fix a bug in a provided buggy function. For explaining, we ask the model to explain a function to us or describe it. And for synthesizing, we ask the model to implement a function from scratch. And all of these are available across those 6 different programming languages: Python, JavaScript, Java, Go, C++, and Rust. And everything is created by humans, manually translated, to ensure that it is really high quality. And the metric we use usually is pass at K. So now we have the data, we have the benchmark. We can finally train a model and have our instruction following code large language model. So we benchmark a few different configurations on the HumanEval Pack. So the baseline being no instruction tuning at all, which is the leftmost bar. And obviously for code fixing, that's suboptimal. It doesn't really work. For code explanation, it doesn't work at all because the model can't follow instructions, so it can't really explain code, so the bar isn't even present. And then code synthesis is also suboptimal. Overall, no instruction tuning leads to poor performance. We find that we get the best performance by combining commit pack FT that we created with OSST, which contains mostly conversational data. Especially for code fixing, we find that commit pack FT is really critical because it contains a lot of samples that have some code before with some bug, and then the commit message describes a fix that was done to address that bug, and then the code after is the fixed version, which lines up very well with this task of code fixing. So we use this recipe to train our final models, OctoCoder and also OctoGX. The difference being that OctoCoder is initialized from StarCoder and OctoGX is initialized from CodeGX2. And so OctoGX is a bit smaller with fewer parameters, and so depending on the inference costs, one or the other might be more interesting for practitioners. Now, we find that Octocoder is the best permissive model on HumanEval Pack. So here across the 6 different languages, but also on the 3 different subtasks. So here we have HumanEval Fix, and then HumanEval Explain, and also the synthesized variant. Now, since this release, many more code models have come out. Some of them might also have very strong performance, but nonetheless, we think that these artifacts are pretty useful. So we've open sourced everything, and I invite you to check it out or also check out the paper. And if there are any issues, feel free to leave us feedback on the GitHub or find other ways to contact us. Thanks a lot.